In this lecture, let's talk about one of the most useful concepts of advanced mathematics, and that is differential forms. Now, like many other advanced math concepts, you have actually secretly been using these differential forms before. Now, what do they give you? Well, they provide you with a method for constructing coordinate invariant expressions, and they help you to simplify certain calculations. Calculations like for curvature tensors in general relativity. Now, they also play a certain role in differential topology, right? But that's not what we're going to talk about. We will be mainly focusing on differential forms and what they are. And at the end, we will talk about some of the physical significance of these differential forms, and we will just very shortly see how are they used in a string theory, right? Okay, so to start with, we will start with that a differential P form. So a differential P form, and that is written as A superscript P, right? So this is how you write a differential P form, and it is simply a 0P tensor. And this is actually completely antisymmetric. So it is completely antisymmetric. Right. Now we can write this in terms of components, and we would have, for example, a zero form, that is p is equal to 0. We would have simply a scalar, right? And this is with no indices. No indices. Then we could have one form that is actually a dual vector, right? A mu. This mu doesn't look so nice. Yeah. So, and then we could go on further. We could have more forms. Two form, for example, would be b mu nu, and we have to remember that it has to be completely antisymmetric, right? And therefore the b nu mu component would be equal to negative of b mu nu, and so that preserves the antisymmetric nature. Now we could also have three form, for example, and this is where I would actually stop. That could be as c mu nu lambda, where we have to again preserve the antisymmetric nature, and that would imply that this c mu nu lambda is equal to c lambda mu nu is equal to c nu lambda mu. And if you note over here, we have just done an even number of indices swaps, and this would further be equal to if we do an odd number of indices swaps. That would put in a negative sign over here, and we would have negative c nu mu lambda, and that would be equal to negative c lambda nu mu, which would be equal to negative c mu lambda nu, right? So this one over here is with even number of indices swaps, and this one is with odd number of indices swaps. So even number of indices swapping, so even swapping, and this one is with odd swap of indices, right? Now we could go further and talk about these in 4 dimensions. So in 4D. Now in 4 dimensions, we will talk about the components of these forms. And so it turns out that a 0 form has 0 components, and a 1 form, for example, will have 4 components. 2 form would have 6 components. Now you might see a pattern over here, but then I'll just tell you that a 3 form actually has 4 components, right? So the pattern actually failed, right? Okay, so it turns out that then this thing C mu nu lambda, where it has more number of indices, right, that actually has fewer components, so less components than the B mu nu, right? So that is a 3 form has fewer components than a 2 form, right? Now to generalize this, we can say that for a P form, so for a P form in D dimensions, we have D P components, right? Now what is this thing that I have written over here? That is simply that dp is equal to d factorial over p factorial times d minus p factorial, right? And so a p form in d dimensions has this many components, right? And it is important to note that these components are independent components, right? Okay, now you could say that what if, because this d minus p might make you want to say what would happen if you have p is equal to d, right? So if the p form is equal to the number of dimensions, then if you recall what is 0 factorial, right, that is simply 1, right? And so in that case, if p is equal to d, we would only have 1 component, right? And in fact this p is equal to d even has a name. It's called the top form, right? So when the number of dimensions and the form number is equal, that is known as the top form. Now at the moment with all of these, let me get rid of these notifications. Yeah, okay, so at the moment with all of this, things might not really seem so special, right? But very interesting things will happen when we consider product of forms. So let me write this down over here. Product of forms, and we consider derivatives of forms and integrals of forms, right? Now first let's talk about the product of forms, which is actually known as the wedge product, right? Okay, now in wedge product we can multiply 2 forms and get another form, and we can do that if we are careful to preserve the anti-symmetry, right? So we have to preserve the anti-symmetric nature of the forms, and then if we multiply 2 forms, we can get another form. And so then we can define wedge product with keeping in mind the thing I just told you, right? Then we have A, P, wedge. Now this symbol over here, it stands for the wedge product, right? Wedge product. So AP wedge product with BQ, right, is actually equal to CP plus Q. This thing over here. Now we can write this in terms of components, and in that case the C would be C mu 1 up to up to mu P plus Q, right? So this many indices, and this is simply equal to A wedge B with mu 1 up to mu P plus Q, right? And then this is then defined as P plus Q factorial over P factorial times Q factorial A, and we have this thing mu 1 up to mu P, right? And then we have B with, now it ended at P, so it should start with P plus 1, right? And it goes up to mu P plus Q, right? And so this is how we define the wedge product, and we have to keep this in mind, that we have to preserve the anti-symmetric nature of the form, and that's why we have this definition, right? Okay, so let's actually consider an example, right? Because maybe this might not seem so interesting to you right now, but if you consider an example where we have, say, example, let's start with P and Q are same, and let's say they are equal to 1. In that case, if you do A wedge B mu nu, that is simply equal to 2 factorial over, now we are using this formula, right? Okay, so P and Q both are 1, so P plus Q is 2, and 2 factorial, then we have P factorial times Q factorial, that would be 1 factorial times 1 factorial, so 1 factorial times 1 factorial, and then A, now note that over here again P and Q are 1, so we would just have mu B nu, and this thing is then simply equal to 2 times 1/2 A mu B nu minus A nu B mu, right? And this thing is then simply equal to, you cancel these 2's out, and you're left with A mu B nu minus A nu B mu. So what does this tell you? This tells you that if you have P is equal to Q is equal to 1, in this case your A wedge B mu nu is simply equal to A mu B nu minus A nu B mu, right? Okay, let me just highlight this quickly. Okay, now we could go further and we could consider an example where P and Q are not equal. And let's do that. Let's take P is 1 and Q is 2. Now, what does this tell you about the indices is that you would have 3 indices on your wedge product. So if you were to take A, wedge B, you would have mu, nu, and lambda, right? And if you have this, then if you go back over here, this formula, right? You will use this formula, we'll add P plus Q just how it is. So let's actually go and apply that. So if we do that, instead of 2 now, we would have 3 factorial over here, 1 factorial times this 2 factorial, right? And then A mu B nu, and this thing will simply be equal to 3 times 1 over 6, so that's 3 over 6 times A mu B nu lambda plus A lambda B mu nu plus A nu B lambda mu, and we'll continue this with let me just quickly check this. We have A mu B nu lambda, A lambda B mu nu plus A nu B lambda mu. Yes, that's correct. And then negative A mu B lambda nu minus A nu B mu lambda minus A lambda B nu mu, right? And let me write that down neatly. B nu mu, right? This is what we would have, and we could quickly simplify this, and upon doing so we are left with 1 over 2, because this 3 1 and this one 2, times A mu B nu lambda plus A lambda. I'm just simplifying the above expression now, so B mu B mu nu plus A nu B lambda mu minus A mu B lambda mu minus A nu B mu lambda minus A lambda B nu mu, right? So I just simplified this term, right? And then I wrote all of this just as it is. Okay, so another thing is, or the another property over here is that if you were to take A wedge B, that is simply equal to minus 1 raised to power P times Q B wedge A, right? So this relationship is important, and it is not really obvious, right? But let's look at this relation and consider an example. So again, in our example, let's start with P is equal to 1 and Q is equal to 1. Now, in this case, if I am supposed to take B wedge A mu nu, right? So I have 1 and 1, so I have 2 indices that are mu and nu. This would be equal to B mu A nu minus B nu A mu, right? According to this thing over here. actually not according to this thing over here, according to something that we mentioned above, right? We did an example over here, right, when we said that P and Q would be equal to 1, and this is what we got, right? Now okay, there's a bit lag in here. Right, now if we have this thing, right, what we can write this thing as is equal to, if you use this relation now, right, your P and Q are 1, so we would have a negative sign outside, and in here I would have A mu B nu minus A nu B mu, right? And this is simply equal to negative A lambda, I'm sorry, I'm calling this lambda, this is wedge product, right? A wedge B mu nu. And so then you can see that this thing is satisfied, right? This relation over here. Now you could do another example with taking P is equal to 1 and Q is equal to 2, but I would say I would not do this for you. I would say that you should do it yourself, right? Do it as an exercise. Okay. And if you go ahead and do that, what you would find out is that simply this B wedge A mu, we would have 3 indices now, mu nu lambda is equal to A wedge B mu nu lambda, right? This is what you would get if you were to compute this one for yourself. Right, now we have talked a lot about wedge product, right? So the product of these forms. Let's move on and talk about the derivatives of the forms, which is actually known as the exterior derivative. And there is a whole branch for this. It's called the exterior calculus, right? Now in here, forms, or at least their components, right, they can vary over space and time. So what that means is if I write B mu nu, what I really mean over here is B mu nu as a function of some x lambda, right? Where again x lambda is our 4 vector. Now, of course, it would be useful to describe how forms vary, and that is where these derivatives jump in, right? Now, we could just use the usual partial derivative, and what is that? That is partial lambda, which is equivalent to partial over partial x lambda. So this is the usual covariant partial derivative, but the object that results using this is actually not particularly nice. So we are not going to use this. On the other hand, if we are actually careful again, and we can make a derivative then such that the derivative of the form gives another form. Now, what I'm saying is, say, consider this form A, P, right? Then D, A is actually a P plus 1 form, and it would have components. So with components, that would be dA mu 1 up to mu p plus 1 is equal to p plus 1 factorial partial mu 1a mu 2 and up to mu p plus 1, right? Now, the exterior derivative has at least three nice properties, right? So the first one is that it satisfies the modern Leibniz product rule, right? So that is that for some A, P, and B, P, we actually have this thing that D A wedge B is equal to dA wedge B plus minus 1 to the power P A wedge dB, right? And now it kind of looks similar to the product rule that you study in your normal calculus, right? But this one is the modern Leibniz product rule. So it's the modern Leibniz product rule. Now the second one, the second property is that you might think that a curved space or in curvilinear coordinates, we would need to use this thing, that is partial mu is something like this. It's a d mu, right? Now, to get back a true tensor form, this is what you would have to this is what you might think that you would need to get back a true tensor form, right? To get back a true tensor form, right? Because of the metric and all, right? But it turns out that due to the anti-symmetrization, even if you include the Christoffel connections, what happens is that the Christoffel connections, they end up cancelling out, right? And this has a meaning, right? And it just means that we have a meaningful tensorial derivative without requiring a metric, right? So these derivatives are defined on and only depend on the topological aspects of space-time, right? And in a later video, I'll talk about the topological field theory as well, once I properly study it. But yeah, so I will actually talk about that in depth as well in a later video. Now, the third property is that it squares to 0. So if you were to do this thing, dA, that would simply give you 0. It vanishes. And since we would have to anti-symmetrize the indices or each partial derivatives, but we already know that partial derivatives commute. So that's why this thing would end up being 0, the square of the exterior derivative. Now, this feature is actually one of the keys to how exterior calculus of differential form leads to topological invariants, right? But then again, more on that in some other video, right? Now, we have talked about the products of these forms. We have talked about derivatives of these forms. What could we talk about next? In fact, I even mentioned this. We could talk about integration, right? So once we have the derivative, then the natural question is how does one integrate, right? So integration. Now, so far we have been looking only at the components of the forms in everything that we did above, right? But here it will be useful to remember that the components actually only arise when we decompose the form into a basis. And that is something like a p, which is equal to 1 over p factorial times this thing a mu 1 up to mu p dx mu 1 dx mu 2 up to, of course, dx mu p, right? And here the differentials anti-commute. Now what that is that if I were to do this thing dx mu dx nu, that is simply equal to negative of dx nu, and that looks like we dx nu dx mu, right? So that is the differentials anti-commute. But you might ask why, right? Well, for that, consider this one, that if you had this 2 form, that is simply equal to 1 over 2 a mu nu dx nu dx mu, right? Over here, yeah, this would be opposite, so nu mu, right? Okay, over here this thing a mu nu is actually equal to negative of a mu nu. So a nu mu is equal to negative of a mu nu, as we had already mentioned that they are completely antisymmetric. So then this would be equal to negative dx mu dx nu, right? And that is why the differentials anti-commute. Also, since u and mu are dummy indices, what we can do is we can exchange these, right? So mu and nu can be interchanged. Now, in fact, if we could consider this thing as dx mu 1 wedge dx mu 2 wedge dx mu 3, and of course keep wedging them up to dx mu p. Here what is the question is that what is so nice about this set of anti-commuting differentials, right? For this, what we could do is consider, let me write down the question, what is so nice about anti-commuting differentials? And to answer this, one should consider the dx dy and transform it to x prime as a function of xy and y prime as a function of xy. Now what then happens is that this dx dy actually transforms as some dx prime dy prime, which is equal to partial x prime over partial x times dx plus partial x prime over partial y times dy, right? we are just taking the derivatives of these things, right? And times for this dy now, we would have partial y prime over partial x dx plus partial y prime over partial y dy, right? And if you could open these brackets, which of course you can, it is equal to partial x prime over partial x, partial y prime over partial x. Again, note that I'm just multiplying all of these, right? Okay, so yeah, then I would have dx plus partial x prime over partial x times partial y prime over partial y dx dy plus partial x prime over partial y prime over partial x dy dx, and the last term would be partial x prime over partial y times partial y prime over partial y dy dy. Again, I have just multiplied these two things, right? Opened the brackets. Now, here we already actually know how the dx dy transforms under the Jacobian, transforms under the Jacobian, right? Hopefully you also know this, and that is simply dx prime dy prime is equal to partial x prime over partial x partial y prime over partial y minus partial x prime over partial y prime over partial x times dx dy, which is exactly what we get if dx dy is equal to negative dy dx. And this only goes to imply that dx is equal to dy, which is equal to 0. And well, we already mentioned above that one of the properties were that the square of the exterior derivatives equals to 0, and that is what we see over here, right? Okay, so now at the end of all of this, the basis of a P form is actually an integration measure over a p-dimensional oriented volume. What I just said it really means is that an expression like the integral of this differential form is perfectly well defined and coordinate invariant. So it is well defined. I don't know if this symbol looks like an integration or a snake. Yeah, it's an integration, right? So it's this integral is well defined and coordinate invariant, which is exactly what we said in the beginning of this lecture. And what I said was that these differential forms, right, they provide us a method for constructing coordinate invariant expressions, right? And so that is what we just found out. Now, at the beginning, I also mentioned that we will talk about the physical significance to differential forms. And so what is that is that there is a natural coupling between the P form natural coupling between P forms and the uh, um, between the P form fields, right? Actually, between the P form fields, that is AP, right? And the P dimensional world surfaces. And these world surfaces that are swept out by it was P minus 1, yeah, P minus 1 dimensional objects, right? And so I don't know if you understood what I said, but let me actually give you an example that if I had P is equal to 1, that is this integral a 1. This is a natural coupling of, so it's a natural coupling of one form a mu to a particle's world line, right? But if, for example, my p is equal to 2, then that is that I will have this integral a 2, and then that is the natural coupling of two form, which is b mu nu to, now this time it would be to a string's world sheet, right? Because strings would be like a sheet rather than a line. Now, in fact, actually, this, to be even more general, this integral b p is a natural coupling of a p form of, and a d p minus 1 brane. And I'll just talk about this, right? Brane's world line, actually. Now, D-Branes, I'll just give you a very, very short definition and tell you what it is. So D-Branes are actually Drishlay membranes, right? So let me write this down over here. D-Branes, or in fact, that is what it stands for, at least. So D over here stands for Drishlay and membranes, right? So it's Drishlay membranes. And if these Drishlay membranes are a class of objects upon which open strings end with some boundary conditions, those are called Drishlay boundary conditions, right? And that's why we have this name, Drishlay membranes, because they are the objects which the open strings end on, right? And the condition has to be the Drishlay boundary conditions, right? Now, in string theory, the equation of motions that we get for string theory, they require that the endpoints of an open string satisfies one of the two types of boundary conditions, one of which is this Drishlay boundary conditions, and that these pins to the endpoints of a string. On the other hand, we have Neumann's boundary conditions, and they correspond to free endpoints. And those free endpoints are moving through space-time at some speed, and that is the speed of light. Okay, so I'm not going to continue this anymore. This is all I have to say about differential forms. And like I said, that they are one of the most useful concepts in advanced mathematics in theoretical physics.